All right, in this video what we're going to be going over is calculating a correlation coefficient by hand, specifically a Pearson correlation coefficient. Now the data that we'll be using for this example is hypothetical data based on 10 individuals. How many hours they spend on social media per day will be our X variable, and their depressive symptoms rated 1 to 10, 10 being the most depressive symptoms, as our Y variable. Now, just like other hypothesis tests, we have this sort of step-by-step process we need to go through: state the hypothesis, set the rejection criteria, calculate the test statistic, interpret it, and then report our results. So let's work through this. Now, the first thing that we're going to need to do, again, is state our hypotheses. And specifically, these are our statistical hypotheses, which would be our null hypothesis, represented by H sub 0. And this says that there's nothing going on, which would correspond to a correlation coefficient in the population of 0. And this would be the Greek letter rho, which really just looks like a P when I write it. And then the alternative hypothesis is that there is something going on. There is actually a correlation in the population. So here we come again. And now it's not equal to 0, indicating that something is going on. So this lets us know that we have a two-tailed test. And here we go. So the next thing that we need to do is we need to actually set our rejection criteria. This is going to work similar to other sort of statistical tests that we have. We're going to have a sampling distribution of some type. In this case, let's say it's Pearson's R. It's going to, with a two-tailed test, have two critical regions, one in each tail, that are each bounded by two different critical values. All right, now to find out what those critical values are, because that's what we're going to compare our observed test statistic against, we need to essentially look up that value in a table in the back of the book. Some textbooks do this based on n, some do it based on degrees of freedom. The one that I'm working out of does it based on degrees of freedom. And the degrees of freedom for a correlation is going to be n minus 2. Now I have 10 individuals, so I'm going to have 10 minus 2 to get me 8. I then use that number to look up the critical value for a two-tailed Pearson correlation test. And that number that I see is actually 0.632. Now it's important to recognize that now that I have a two-tailed test, this critical value is going to be 0.632. And this one over here is actually going to be negative 0.632. So what this comes down to is if the R observed, or R, our Pearson correlation coefficient, is greater than 0.632, placing it in this critical region, or it is less than negative 0.632, placing it in the left-hand critical region, then we end up rejecting that null hypothesis. So now that we've got our rejection criteria set, now it's time to actually calculate our test statistic. All right, so first and easiest thing to do is write out all the information that you'll need. The first of that is going to be the formula for Pearson's R, which is R is equal to the sum of products, which is SP, which is a measure of covariance, divided by the square root of the sum of squares of x times the sum of squares of y. So how much do the two variables vary together versus what is their total degree of variation? Sort of giving us this ratio of how much of their variation is together. So we don't have those values given to us in the problem, but there are formulas for each of these. So the next thing I would do would actually be to write out all of these. So the sum of products is equal to the sum of x times y. specifically all the products of s and y, or x and y added together, minus the sum of the x scores times the sum of the y scores divided by n, and then the sum of squares of x, which would just be the sum of the squared x scores minus the sum of the x scores squared divided by n, and then SSY, which would be the sum of the squared y scores minus the sum of the y scores squared divided by n. Now, the next thing you should do to help yourself is actually give yourself a couple more columns in this table here where you can create all of those products and all of those squared scores. So if we just extend these lines a little bit, then we can do this. So we know we're going to need all the squared x scores and all the squared y scores. Oop, it's not a very good y. And then all of the products of x and y. So now it's just a matter of, okay, 4 squared is 16, 5 squared is 25, 4 times 5 is 20, and then so on all the way down the table. All right, now that we have all of those numbers, we know we're going to need the sum of all of these columns as we go through. So now it's just a matter of adding up this entire column and then writing it down, adding up this column, so on and so forth. The easy way to do this is just to add up all the numbers once and then do it again. It's really easy to have one keystroke error, so just do it twice and check yourself. And if the numbers don't match up, do it a third time. And then again for each of the columns. We've got those all laid out, and I actually did it ahead of time, but you know. So now it's actually time to go through and work these. Now we could essentially work from the bottom back up because this is the last formula we'll work with, because essentially the output of each of these formulas goes into this one. So starting at the bottom, the sum of squares of y is sigma y squared, 214, minus y, the sum of the y scores squared, 40 squared. And then I have an n of 10. So looking at this and working through it, 40 squared is 1,600 divided by 10 gets me 214 minus 160, which gets me a final value of 54. Now I can go ahead and move up to the sum of squares of x. So I need sigma x squared, 113, minus sigma x squared, so the sum of all the x scores, 27, squared, divided by the number of scores that I have, which would be 10. 27 squared comes to 729 divided by 10. So 113 minus 72.9 gets me a final score of 40.1. Now we're up to the sum of products. So first score we need is sigma xy, 149, minus sigma x times sigma y, which would be 27 times 40, divided by the number of scores I have, which would be 10. So looking at this now, we have 149 minus the product of 27 times 40, which is 1080 divided by 10, which gets us 149 minus 108 for a final value of 41. So now we take each of these numbers, the sum of squares of y, the sum of squares of x, and the sum of our products, and we plug them in up here. So our sum of products came out to be 41 divided by the square root of the sum of squares of x, 40.1, times the sum of squares of y, 54, so bringing this down here, we're going to have 41 divided by the square root of that product, which comes to 2,165.4. The square root of that number comes to 46.53 and change. Giving us a final value of 0.88. So here, excuse me, is our final value for our Pearson correlation. The next step would then to actually interpret it, and so we would actually come up here, and I'm actually going to need a new sheet of paper for this unless I can cheat. And come down here. Alright, so our R observed is equal to 0.88. And if we look here, if R observed is greater than 0.632, which it is, or less than negative 0.632, then reject our null hypothesis. So in this case, we would reject the null hypothesis, letting us know that we have a significant correlation. All right, now it's great that we found this out, but in order to have it, really affect the world at all, we have to be able to communicate these findings. So in terms of reporting for Pearson correlation, there are two standard ways. The first is to have R, for Pearson's R, the degrees of freedom in parentheses, which in this case would be 8, and then our correlation coefficient, which by convention is typically always rounded to 2 decimal places, and then a statement about our p-value. In this case, we used a two-tailed alpha of 0.05, and there we go. Now, another way to do it is to state that R is equal to plus 0.88, and then supply the n, and this plus indicates that it's a positive correlation, by the way, of 10, and then another p-value statement. Now, either way you do it, there is a specific way this needs to fit in the sentence in the text. They both need to be separated from the rest of the sentence by commas or parentheses. And also, critically, they can't play what's called a grammatical role in the sentence. In other words, the sentence must not depend upon these reportings, these statistics, to actually make it a complete sentence. You have to be able to read that sentence independent of these and have it work. So, as an example, using this one here, there was a significant positive correlation between the number of hours a person spent on social media and their depressive symptoms. Now, some things to point out. The word significant indicates that we rejected the null hypothesis. So you should not say that we rejected the null hypothesis. The word significant means that. It means it's statistically significant, not necessarily that it's important per se. Also note that I could put a period right there. And this is a complete, grammatically correct sentence. However, if you are writing in an academic publication, you also then need to essentially provide the evidence that supports this sentence. Note that I use the word supports the sentence. It does not complete the sentence. So in this case, I'm going to use this first means of reporting right here, where I then switch this period to a comma, and then it is R to indicate persons R, parentheses, and then I need my degrees of freedom, which is 8. Close the parentheses, and then I provide my R value rounded to 2 decimal places. And then I make a statement about my p-value. In this case, it is less than my alpha level, meaning that there's less than a 5% probability of getting this test statistic by random chance. And there I go. Now, one thing to note that's not necessarily statistics, but more sort of the research methods and sort of how we make use of this information. And that's that you need to be careful. Yes, there's this positive correlation, but that doesn't mean social media is making people depressed. It could be the case that depressed individuals tend to be on social media more because they're not engaging in other activities. So you can't determine directionality and causality from a simple correlation like this. All right. Good luck. Happy trails. Have at it.